Hi, my name is Abbas Askar and I'm a postdoctoral researcher at Lund Observatory in Sweden. In this talk, I will be presenting some very preliminary results on formation of LISA binaries and intermediate mass ratio inspirals in galactic nuclei. At the center of many galaxies with stellar masses between 10 to the 8 to 10 to the 10 solar masses, there exists a nuclear star cluster. This is a dense star cluster with an effective radii of a few parsec, and the formation mechanism remains a matter of debate. They may form through accretion and merger of star clusters, or they could also form from gas accretion, which leads to then in situ star formation. Nuclear star clusters are often accompanied by supermassive black holes, which can be between 10 to the 6 to 10 to the 10 solar masses, such as in galaxies like the Milky Way and M31. However, there's another galaxy in the local group which contains a nuclear star cluster but no supermassive black hole. This is M33. It has a nuclear star cluster of about 2 million solar masses, but the upper limits on a central black hole mass are about 1500 solar masses. And this raises a key question: which comes first, a supermassive black hole or a nuclear stellar cluster? It may be possible to form a nuclear star cluster before a supermassive black hole. If infalling stellar clusters aggregate to the galactic center due to dynamical friction, they can form an NSC. It is possible that many of these dense stellar clusters that merge with the galactic center have already formed an intermediate mass black hole inside them. There are various mechanisms by which intermediate mass black holes of a few hundred to 100,000 solar masses can form inside stellar clusters, such as through runaway mergers of stars or black holes, or through other processes such as binary coalescence, mass transfer events, tidal capture, disruption of stars, and they may also form through growth of stellar mass black holes by accretion of interstellar gas. These stellar clusters can then essentially deliver their intermediate mass black holes to the galactic center. And these intermediate mass black holes may then seed the supermassive black holes. So the idea presented here builds on results from direct n-body simulations in which we merge 3 stellar clusters, some of which contain intermediate mass black holes. What we found is that in the case where we have 2 or more intermediate mass black holes, we form an IMBH binary, and this binary hardens as it gets more eccentric due to interactions with surrounding stars, leading to the efficient merger of the binary black hole due to gravitational wave radiation. The retention of the merged black hole will depend on the recoil kick which the binary receives, which the black hole receives following the merger. If this recoil kick is less than the escape speed of the nuclear star cluster, then the merged black hole can be retained in there, and then it may grow on to become a supermassive black hole. So what we've done as a follow-up to the previous work is we have done a population synthesis study. What we do is we sample galaxy stellar masses, we account for their nucleation fraction, and find a corresponding nuclear star cluster mass. Then we randomly draw stellar cluster masses and aggregate them until we can reproduce each nuclear star cluster mass. We also assign each stellar cluster a probability for bringing along an intermediate mass black hole based on some Monte Carlo star cluster simulations that we've done before. And if the cluster can bring along an IMBH, we also provide an estimate for its IMBH mass when it merges with the galactic center. So the next step is, using these ingredients, we roll the dice. We can then find how many intermediate mass black holes can potentially be delivered to nuclear star clusters with different masses. For NSC masses where we have more than one IMBH delivered, we can determine the likelihood of retaining the merged black hole following mergers. And we also consider the case where the black hole can grow inside the nuclear star cluster after it has been delivered. So we sampled about 200,000 galaxies which had stellar masses between 10 to the 7 to 10 to the 12 solar masses, and they also had an NSC. On this figure, in this heat map, what you see is the number of intermediate mass black holes delivered in nuclear star cluster in these mass bins. what we essentially find is that for low nuclear star cluster masses, we only need 1 or 2 clusters aggregated to reproduce their masses, and therefore the likelihood of delivering many IMBHs decreases. But as you go up in NSC masses, you need to aggregate more stellar clusters to form the NSC, and then the likelihood of one of those clusters bringing along IMBH increases, and therefore this number goes up. In this talk, I will be focusing on the models in which we deliver 2 intermediate mass black holes later on. But essentially what we find is if we look at the NSC masses versus the massive black hole masses that are delivered, the blue points here showcases where no intermediate mass black holes are delivered, the orange ones are where 1 is delivered, and the purple one is where 2 are delivered, and the yellow ones are where more than 2 are delivered. So for the results here, I'll focus in on the 2 intermediate mass black hole NSCs, because we imagine that there the intermediate mass black holes will end up in a binary at the center. We also then consider these pathways for growth. And essentially what we are also considering is that once these binaries at the center will merge due to gravitational wave radiation, we are only retaining the merged black hole if the mass ratio of the merging black holes is less than 0.15, which corresponds to recall kicks of a few hundred kilometers per second, which can still be less than the escape speed of the nuclear star cluster. If we allow one of the black holes to grow before the next one is delivered, then this alters the mass ratio of the merging black holes, and thus it leads to a higher occupation fraction of a seed intermediate mass black hole at the end. Also, allowing for growth allows us to reproduce observed black hole masses. So black holes could grow in the center of galaxy through tidal disruption of stars or through gas accretion. Now let's come to the point models where 2 intermediate mass black holes are delivered. We had about 10,000 such galaxies. What we do next is we determine the properties of the merging binary black holes using their masses that we have for them, and also by using the delivery time of the second black hole in the nuclear star cluster. If we assume that the merger takes place close to the time when the second black hole is delivered, or shortly after the second black hole is delivered. Using this, we can estimate the redshift, which corresponds to the cosmic merger time. And with this redshift, we can calculate the luminosity distance and the co-moving distance. And we can then, using the masses, estimate the gravitational wave frequency when the 2 black holes are very close to merging. Using this frequency, we can also estimate the strain and then convert that into characteristic strain using these formulae. Now we have the characteristic strain for our merging binary black holes and their frequency as well. And then we can compare this with the LISA sensitivity curve to see whether these merging binary black holes will be detected. So on the left here, you see the case where we do not consider any growth for the first black hole. So we deliver one black hole, we deliver the next black hole, and we merge them. And what we find is that there are a considerable number of these sources which will be above the LISA sensitivity curve and will have a high signal to noise ratio at the time of merger. About 15% of these 10,000 cases will be LISA visible. However, if we allow for the first black hole to grow before merging with the next one, then we significantly alter the frequency distribution by increasing one of the masses, and this increases the number of detectable sources to up to 65 to 70%. And essentially, by making the first black hole more massive, we are increasing the characteristic strain as well as decreasing the frequency, leading to better signal to noise ratio for these binaries. If we now look at the distribution of the same distributions that we looked at earlier, but now the colors represent the chirp mass, you find that the brighter and the more lower frequency sources are the ones which have a higher chirp mass. And by allowing for growth, we have increased our chirp mass distribution, populating this area in the frequency sensitivity curve highlighted with the pointer. So This essentially allowing for growth of the black hole with a reasonable assumption of a doubling time of about 300 mega years. We are able to get this spread, and here we show the mass ratio of distribution for the case where we have no growth, and then in the case where we allow growth with a doubling time of 300 mega years. The choice for this time is that because the doubling time of a black hole accreting at Eddington rate is about 40 mega years, 30 to 40 mega years, and then if we assume that the black hole is accreting at 10% of the Eddington, then it would double its mass in about 300 mega years. So allowing for growth, it not only increases the Chern mass, but it also results in this large spread in the mass ratio distribution, which you can see in the blue histograms here. Now, if you look at our M1 and M2 distribution, in the case where we consider no black hole growth, our typical black hole masses range between a few thousand to a few 100,000 solar masses. But when we allow for the black hole to grow before it merges with the second one, then we can have black hole masses in the supermassive black hole regime going from 10 to the 6 to up to 10 to the 8 solar masses. And then they can merge with these intermediate mass black holes ranging between 1,000 to 100,000 solar masses. And essentially, based on our assumptions about the nucleus star cluster assembly and the time at which the stellar clusters are merging with the galactic nuclei, we find the following redshift distribution for these mergers. We find that most of them will occur at redshifts of between 1 to 2, but obviously this does depend on the assumptions we have put into the model. So the next step is to improve the treatment for the determination of the observable properties of these merging systems, better frequency and strain calculations and how they evolve with time, and then also explore how our initial assumptions will affect the results concerning the IMBH masses, their formation and growth, and we'll also check the merger properties of in the nucleus star clusters where more than 2 intermediate mass black holes are delivered. And then we would also like to estimate potential merger rates for the case with and without the growth of black holes. So in summary, the central idea presented in this talk is that a nucleus star cluster can form before a supermassive black hole through the merger of stellar clusters, which could potentially have formed intermediate mass black holes. These, if 2 or more intermediate mass black holes are delivered to the center of a galaxy, they can form an IMBH binary. We find that this will merge due to gravitational wave radiation, and that about 15% of such merging binary intermediate mass black holes will be detectable with LISA in the case where we do not allow the black holes to grow. If we allow the first black hole to grow at a moderate doubling time of about 300 mega years, then we can increase the number of LISA detectable binary sources to about 65%. And this growth of the black hole will also increase the number of intermediate mass ratios in spirals. So the key conclusion is that the detection or non-detection of these predicted merging binary black holes in the galactic nuclei with LISA will allow us to better constrain the formation and growth of mechanisms of supermassive black holes at the center of galaxies. Thank you for your attention. If you have any comments, questions, please feel free to contact me. Bye.